Okay, so in problem number 26, they describe a coil of diameter 5 centimeters here with 20 turns and some resistance in there. So I'll go ahead and put the 5 centimeters on there, but just note that the coil also has some resistance and some number of turns as the problem states in there. We'll just sort of keep that sort of general for this discussion here. And what happens with this coil here is it's actually in a big magnetic field, which it says is perpendicular to the coil itself. So if I was going to draw the magnetic field in this problem here, it would sort of look like this. These big blue lines here would be the magnetic field lines. So the coil is just completely immersed in a big magnetic field. Now I know this figure looks a lot like a solenoid, but keep in mind this isn't the magnetic field generated by the solenoid. It looks like a solenoid and probably is a solenoid, but it's just a coil at this point, which is immersed in some external magnetic field, which is sitting there like that. Now the crux of the problem is that this magnetic field that is sitting in is not a constant. It's 0.02 T plus 0.01 T squared. In other words, the magnetic field has this funny time dependence of it here. Now the problem says something about sketching it, which you can do. It's probably not the most critical part about the problem right here, but if you wanted to plot B as a function of time, it would just be some function sort of increases like that. You can see it's some linear term, some quadratic term that increases as a function of time. So, okay, the important part for Faraday's law is that the magnetic field is not constant. So this solenoid or this coil is in a magnetic field that's not constant. It has some time dependence here. In fact, if you wanted to do it real quick, dB dt then is 0.02 plus 0.02 times t. I mean, there's the time dependence right there. There is a dB dt. So in terms of working out Faraday's law now, what is the induced current in this thing? Well, it all is going to stem from Faraday's law. In particular, you know Faraday's law, the induced EMF is minus the number of turns times the change in the magnetic flux with respect to time. That's good old Faraday's law. No big surprises there. What is it for this coil that's sitting in this magnetic field? Well, it's going to be the number of turns of the coil, that N that we discussed very early on in the problem here, times the area times dB dt. That's it right there. The area is the area of the coil, which is not changing right there. I guess that's one more parameter I probably should have put up here. But this coil here has sort of this cross-sectional area A in there, which is sort of the area of the front face of the coil. If you imagine this thing looking like a big toilet paper tube or what have not in there like that, however you want to think about it, there is some cross-sectional area. That would be this A. That's the area that the flux is going through, of course, multiplied by the number of loops N right there. And so that's sort of the key parameters of the system there. Now, I think you have everything you need to sort of put this thing together here. I'll just take it a couple more steps and let you finish here. But the induced EMF then would be the number of turns times the area. That's going to be pi times r squared. The diameter is 5, so it's 0.05 divided by 2 squared, something like that. That's the area right there. And now the dB dt, well, we did that. It's 0.02 plus 0.02 times t, something like that. So this is the induced EMF in the coil. So it's sort of a big, ugly expression there. I think you can probably work on a tad bit. Induced EMF is minus n times pi 0.05 over 2 squared. You can pull a 0.02 out of this thing, just get a 1 plus t like that. So this expression here, if you look at it now, is the induced EMF in the coil because of that changing magnetic field. So it's all in there. The dB dt has its time dependence in there and so on. So this would be the induced EMF in the coil. And if the problem happens to be asking for the current, which a lot of them do now, that's just related by Ohm's law because the coil is just sort of some ohmic device like a resistor, some wire that has some resistance, so it's going to follow Ohm's law. So the current then is going to be the induced EMF divided by the resistance. So in other words, you take this long expression and divide it by R, that'll give you the induced current. So I think you can probably handle a problem from there, plugging in the turns and whatever, and I think the next part asks for what time, the EMF at a certain time. Well, there's your time variable right there. You can just plug in whatever time it's after, and I think that should do it.